Hi, I'm David Mehrle. I'm a PhD student at Cornell University working with Inna Zakharevich. You can find a link to my website in the description below this video. I work in equivariant homotopy theory. Specifically, my thesis is on commutative and homological algebra in the category of Mackey functors. Although computations in equivariant homotopy theory are done with Mackey functors, many aspects of their algebra have not yet been developed. Here, I will share results from two projects of mine in the algebra of Mackey functors. Before I dive into my projects, I want to explain some of the objects in equivariant homotopy theory by analogy to their non-equivariant counterparts. Here, G is always a finite group. Non-equivariantly, spectra have homotopy groups. Genuine equivariant G spectra instead have homotopy Mackey functors. The category of Mackey functors is abelian enclosed symmetric monoidal. When G is the trivial group, the category of G Mackey functors is equivalent to the category of abelian groups. In this sense, Mackey functors generalize abelian groups. Non-equivariantly, there is only one commutative operad. Algebras for this operad in the category of abelian groups are commutative rings. Equivariantly, there are many different commutative G operads. We call these n-infinity operads. Algebras for different n-infinity operads give us several different notions of commutative ring in the category of Mackey functors. The two most common are green functors and Tambara functors, but there are many others. In general, we call an algebra for an n-infinity operad in the category of Mackey functors an incomplete Tambara functor. Finally, the appropriate generalization of the integers to the equivariant setting is the Burnside Mackey functor A. This is the unit for the symmetric monoidal structure on the category of Mackey functors and the initial incomplete Tambara functor. The first project I want to talk about is joint work with Mike Hill and JD Quigley. You can find our preprint on the archive. A link is in the video description. Here's an algebraic fact we take for granted. Z joint X is a free Z algebra on a single generator, but it's also a free Z module with basis 1, x, x squared, etc. The object analogous to Z joint X in equivariant algebra is a free O Tambara functor on one generator, where O is an n-infinity operad. Now, since we are working equivariantly, we have to say how this group interacts with the generator, which is done by specifying a G orbit G mod H. This object, the free incomplete Tambara functor on a single generator, has a universal property analogous to the universal property of the integers. In this project, we ask, is the free incomplete O Tambara functor on a single generator free as a Mackey functor? If not free, then flat is often good enough in homological algebra. Is it flat? Here's our first theorem. If H is a normal subgroup of G, and the n-infinity operad O satisfies a combinatorial condition, then this free incomplete O Tambara functor is flat. If G is solvable, the converse holds as well. Notably, this theorem shows that the statement we desire is not always true, but we hope that the free incomplete Tambara functor is often flat, even if it is not always. So we ask, how often do the conditions in this theorem hold? Our second theorem says that the conditions of the previous theorem are very rare. In particular, among all triples G, H, O of a finite group G, subgroup H, and n-infinity operad O for G, the free incomplete O Tambara functor on a single generator is flat with probability 0. This gives us the slogan, the free incomplete Tambara functors are almost never flat. So can we fix this? Our third theorem says that if we invert a single element in the Burnside Mackey functor A, the result is that free incomplete Tambara functors over this localization are always flat. However, this localization is quite destructive. An interesting follow-up question to this theorem might be to ask what happens when we invert other elements. The second project I want to discuss is joint work with JD Quigley. To motivate this project, we begin with K-theory. One of the most successful techniques for studying K-theory has been trace methods. In its most basic form, trace methods studies K-theory by analyzing the image of the trace map in Hochschild homology. For rings with involution, there's also a C2 equivariant version of the trace map. But for more general rings with a group action by ring homomorphisms, we don't know what the target of a trace map should be, despite recent interest in G-equivariant K-theory. In this project, we are trying to fill this gap. One clue for what this object should be comes from the Hochschild-Constant-Rosenberg theorem. Classically, this identifies Hochschild homology with wedge powers of the Kähler differentials for smooth algebras. Mike Hill has defined a genuine equivariant version of Kähler differentials for incomplete Tambara functors, so we investigate an HKR theorem for incomplete Tambara functors. Here's what we've learned. For a morphism of O-Tambara functors from S to R, there is a surjection from the first Hochschild homology to the module of genuine Kähler differentials. This is an isomorphism when S and R are green functors, but when S and R are not green functors, this need not be an isomorphism. For our counterexample, when S is the Burnside functor A and R is the free C2 Tambara functor on a generator at level C2 mod C2, Hochschild homology is not the same as Kähler differentials. Given this counterexample, an interesting question to ask is how we should modify Hochschild homology for Tambara functors, such that the first Hochschild homology always agrees with the Kähler differentials. Thanks for watching. If you want to learn more, please feel free to email me or visit my website. A link to my website is in the video description below.